In this presentation, we're going to look at continuous random variables and the joint probability density function and modeling the relationship between the two. So let the random variables xy have the joint probability density function. I'm going to just say PDF for probability density function from now on, PDF. Okay, so f of xy, okay, now you just notice that it's lowercase f, and also we have the subscripts there, x and y, just to specify which variables we're referring to there. Okay, and this is the expression for the joint PDF, the joint probability density function. It's exp, the exponential of of minus x plus y in brackets there. Okay, so you could actually just write it as e minus x minus y also if you want, where this is important, this bit here. X is greater than 0, y is greater than 0, that's all. So they're positive numbers. The lower bound is 0, the upper bound is infinity. Okay, so it's the range of possible values for both x and y is 0 to infinity. Okay, so that'll become relevant later on. So derive the marginal probability density functions of x and y, and hence, given reasons, state whether or not the two variables are independent. And later on, what we're going to do is find the joint cumulative distribution function f of xy, where we're talking about capital F there. So we'll just come back to that shortly, but that's capital F there. So essentially, be careful about capital F and lowercase f. So what we have here is we start off both the same way in both cases. Okay, now essentially what we have there is the joint probability density function, and when we want to find the marginal distribution of, let's say, of f of x and f of y, essentially what we do is we integrate the joint PDF, the joint probability density function, with respect to the other variable. So in this case, what we do is we integrate with respect to dy, or we integrate with respect to y, and this we integrate with respect to x. So we have dy and dx there. Okay, so the limits are important as well. Now we took a moment there just to actually specify that the upper and lower limits are 0 and infinity respectively, and that actually applies in both cases. So it's very similar the whole way through for both. So that's why I'm sort of doing both together. Okay, now so this is the joint PDF there. Okay, e to the minus x minus y. Okay, now essentially what we can do here is we can treat that as a multiple. E to the minus x as a product of two different terms. Okay, so we're using our knowledge of powers and logs and so on to help us out here. So essentially what we can do is treat e to the minus x as a constant and bring it out and just treat it separately. And then what we will do there is just get the integral of e to the minus y with respect to y. Okay, and when we do that, it's essentially what we just end up with is minus that. Okay, our integral limits are 0 and infinity. Okay, so what we have now is a definite integral. Okay, now this is important, this part. So I'll just do it over here. E to the minus infinity we treat as 0. Okay, e to the power of 0 is also always going to be 1. Okay, so essentially what we end up with is this when we evaluate this out entirely, this expression here, we get 0 minus 1, okay, which is just equal to 1. Okay, so essentially this entire expression here just becomes 1. So we end up with e to the minus x times 1, which is just e to the minus x. So the answer to this one, this part here, what is the marginal PDF of this? And it is simply e to the minus x. Okay, so I'll just rub out everything else there just to sort of declutter a bit. Okay, so that is our answer there, e to the minus x. Now, working the same way, we're applying the exact same logic to finding the marginal PDF of y. Essentially, we're just swapping x and y out, or we're just swapping the importance of x and y. So e to the minus y is treated as a constant. We're integrating e to the minus x with respect to x, and we get e to the minus x. The limits there are infinity and 0 again, so it just works out the same way. This turns out to be 0 minus 1 when we evaluate that at infinity and 0. That just gives us e to the minus y times 1, which is e to the minus y. Okay, so that is the marginal PDF, the marginal probability density distribution functions, density functions, I had to write the first time, of x and y. So we'll move on to the next part here. Are they independent? Well, actually, yes, they are, because essentially if we multiply the marginal PDFs by each other, essentially what we will get is an expression that is equivalent to the joint PDF. So in that case, we can say that they are independent. X and Y are independent of each other. Okay, so that's just a sort of little definition that you might get asked. It's important to remember, are they independent or not, and how do you show it? Okay, so what we have to do now is find the joint cumulative distribution function, and this is capital F of x. Okay, capital F of x and y. Okay, so now this is important, this part here. This is a sort of we actually should have two integrals here. So we should have one for x and one for y. Okay, two integrals there. And so because we're using x and y as the limits of our integration, what we'll do here is just actually replace x and y in our joint PDF with just different placeholder variables. We'll just pick u and v just for the sake of simplicity. Okay, now so u would correspond to x and v corresponds to y. And essentially what we want to do is we don't want to use x and y, because when we use these, when we put in the limits of integration, that it will become an expression in x and y. So that's the point of using something other than x and y. Okay, so this is what we want to do here. Okay, now essentially in this particular instance, what we can do is separate it out into two distinct parts. Essentially, just when we integrate it out, so essentially what happens is, because we can split e to minus u minus v into two terms, e to the minus u times e to the minus v, we can split our expression, our integral there, into two distinct integrals. Okay, we just totally separate the two entirely. Okay, such that we have two distinct integrals. So we have, in both cases, it's e to the minus something that we're integrating. Okay, e to the minus u du and e to the minus v dv. So just like we had before, we end up with minus e to the minus u, where the limits of integration are x and 0, e to the minus v, minus e to the minus v, and again integrated from 0 to y. So when we work that out, this is what we get here. Okay, 1 minus e to the minus x times 1 minus e to the minus y. So that is f of x, y. Now this one actually was a little bit simpler, easier than usual, partly because this expression here was so easy to work with. So I'll just leave that down a bit, and yeah, that's our answer there. So we'll leave it there.